Alice, Bob, and Eve explain the Deutsch-Jozsa algorithm.
I'm trying to figure out if this coin is fair or if it always lands on the same side. I've flipped it 10 times so far.
What you're doing reminds me of the Deutsch-Jozsa algorithm, one of the first algorithms to demonstrate quantum advantage.
The Deutsch-Jozsa algorithm is such an elegant example of quantum computing. It solves a problem with certainty in one step that would require multiple steps classically.
How does my coin flipping relate to a quantum algorithm?
Imagine you have a mystery function that takes an input and returns either 0 or 1, like your coin flip. The function is either constant, always giving the same output regardless of input, or balanced, giving 0 for exactly half the inputs and 1 for the other half.
Think of this switch box with two buttons. When you press either button, a light either turns on or stays off. If the box is constant, both buttons do the same thing. If it's balanced, one button turns the light on and the other keeps it off.
To figure out which type of box it is, I'd need to press both buttons.
Exactly. Classically, to be 100% certain whether a function is constant or balanced, you might need to check half the possible inputs plus 1. For a function with many inputs, that could be a huge number.
But the Deutsch-Jozsa algorithm can determine whether the function is constant or balanced with just one quantum evaluation of the function.
One evaluation? How is that possible?
It uses quantum superposition. First, it prepares qubits in a special state that represents all possible inputs simultaneously. Then, it applies the mystery function to this superposition.
Due to quantum interference, if the function is constant, the qubits end up in one state. If it's balanced, they end up in a different state. One measurement tells us which is which.
So instead of checking inputs one by one, quantum computing lets you check all possibilities at once?
That's the core idea. The algorithm prepares an equal superposition of all possible inputs, applies the function, and then uses a clever interference trick called the Hadamard transform to distinguish between constant and balanced functions.
It's like if instead of flipping your coin repeatedly, you could put it in a quantum state of all possible flip sequences at once, and then extract just the information about whether it's fair or biased.
Is this algorithm useful for real-world problems?
The original Deutsch-Jozsa problem is mostly pedagogical. It clearly demonstrates quantum advantage, but doesn't solve practical problems directly. However, it laid the groundwork for more practical algorithms.
It showed the power of quantum parallelism and interference, concepts that underpin more useful algorithms like Shor's factoring algorithm and Grover's search algorithm.
So while I'd need multiple coin flips to determine if my coin is fair, a quantum computer could theoretically tell me with just one quantum operation. That's remarkable.
That's the magic of quantum computing. Problems that would require many steps, classically, can sometimes be solved in dramatically fewer steps, using quantum effects like superposition and interference.